All right, this is a video on absolute value functions, and we'll start with an introduction and then do a few solved examples. So I want to remind you of the definition of absolute value. It's a piecewise function, which means it has a couple pieces to it, or it could have more, but in this case it only has two. So the absolute value of x means that it's equal to x if x is greater than or equal to 0, or it's equal to negative x if x is less than 0. Really what that means is if x is a negative number, we multiply it by a -1 to turn it into a positive number. And we can graph that function up. So in other words, if x is going to be -3, here we're graphing y equals the absolute value of x. Y would be 3, 2, 1, 0. And if x is positive, the y value is equivalent to x. So we can plot those points, and you'll get a linear pattern with a negative slope in quadrant 2, and then a linear pattern with a positive slope in quadrant 1. So that's what this guy is going to look like. So that's a classic example of the parent function of the parent absolute value function. Y equals the absolute value of x. Unrestricted domain, but its range is y is greater than or equal to 0. We could graph some more complex versions as well. We could take the absolute value of x and then add 2. So this would be 5. This would be 4, 3, 2. And then we have some symmetry, right? So this would be 3, 4, 5. Just to be clear what we're doing, say for this one right here, take the absolute value of x, turn it into a 3, and then add 2 to get the 5. So we could plot those values as well. -3 up 5, 2, 3, 4, 5. And then we have that same pattern that we saw in the earlier graph. So this is a parent function of the absolute value graph that has also been shifted vertically by 2. Okay, we can do some more complex shifting as well, and this will get us into thinking about what standard form looks like. So we could subtract 3, then take the absolute value, and then add 2. So -3, starting with this guy, subtract 3 is -6, absolute value is 6, add 2 is 8. -2 goes to -5, goes to +5, goes to 7. -1 goes to -4, goes to +4, goes to 6. You got to be careful. Just don't just assume this pattern keeps going, okay? Because eventually something interesting is going to happen. 0 goes to 5. 1 goes to 4, 2 goes to 3, 3 goes to 2, and then we're actually going to continue this a little bit. Let's continue this with x equals 4, 5, 6, and this will help us see what's going on a little bit. 4 minus 3 is 1, absolute value is 1, plus 2 is 3. So this pattern will keep going back up, or will sort of bounce back up after it hits that vertex. I'm going to plot roughly these points right here so you can see the pattern. Over 0, up 5. Then down 4, up 3, up 2. And then it starts increasing again. Okay? Whoops. Let's get a good line drawn in there. There we go. And another good ray drawn in here. There we go. So I hope you can see maybe that this point got moved over 3 and up 2. And we'll look at standard form in a moment, but it comes from these pieces of the equation. Got moved over 3 and up 2. Vertical stretch, we can multiply an absolute value function by a number as well. And so this will turn into a 6, 4, 2, 0, and then 2, 4, 6. So this is going to just vertically stretch my function. -3 up 6. 1, 2, 3, 4, 5, 6. Up 4, up 2, up 0. And then we have that symmetry that we've been seeing. Okay, try to make some nice straight lines. Okay. We can additionally, let me color coordinate, we'll have both of these on the same set of axes. So here's my purple one I just did. And now let's do an orange one here. We can compress, and then this will also flip because of that negative sign, that -0.5 as well. So let us make an X and a Y column for my table. And let's just start with a -3, -2, -1, 0, 1, 2, 3. Okay, so we can take the absolute value, multiply a half, and then multiply it by a -1, or multiply by -1/2, right? So this is -1.5. This is going to be -1, -0.5, 0, and then we'll have the same symmetry we've been seeing, -1, -1.5. So we can graph these guys over here as well, -3 down 1.5, and then continue that pattern up to the origin. Same on the other side. So this is an example of an absolute value function that has been vertically compressed and then additionally flipped vertically across the x-axis as well. So here's standard form, and let's talk about what each of these guys do. A is dealing with a vertical compression or the vertical stretch. And it's a vertical compression if the absolute value of A, in other words, not caring about the sign of A, just caring about the magnitude of A, is greater than 1, less than 1. And it's a vertical stretch if the absolute value of A is greater than 1. Okay? And then additionally, if A is less than 0, we get a vertical reflection. So that's a reflection across the x-axis. Okay, so an up-down reflection. And then lastly, the vertex, and I just abbreviate V for vertex. I write vertex in this form with an ordered pair. The vertex will be H and K. And students always forget, and I sometimes forget as well, that that's a subtraction sign right there. So we're subtracting the value of H, and then we're adding on the value of K at the end. Okay. So for example, if we have something like y equals 3 times the absolute value of x plus 2 minus 5, the vertex will be -2 and -5. Okay, and it became a -2 because we changed that x plus 2 into an x minus a -2. We want there to be a subtraction in there. All right, we could identify some transformations, and I am not going to actually graph these right now. I'm just going to identify what the transformations might be. Okay, so this 3 is going to give us a vertical stretch 3 times. So we're going to have a pretty skinny V, vertically stretched. So 3 will give us a vertical stretch. And then the -5 will affect the vertex. So we will have a vertex at 0, -5. You can also think of this -5 as being a downward shift. And then secondly, we have a couple different things going on here. We have a negative out front, and then we have a +2 inside. Okay, so that +2 will give us the vertex is going to be -2, 0. Remember, we flipped that sign, kind of forced there to be a subtraction in there. We're subtracting, in this case, the -2. You can also think of this as a leftward shift. And then the negative out front, what that's going to do is a vertical reflection. Okay, and it's not going to change any sort of a stretch or compress. Let me actually I changed my mind. I do want to graph one of these guys. I think we have some time to do so. So let's graph this first one. So we have a downward shift and then a vertical stretch. So if you can kind of think about this process in your mind about how this is working, it can go a lot more quickly and you won't need to plot points. So we have a vertex at -5 on the y-axis, and then we have a vertical stretch of 3, meaning the positive arm of my function will have a slope of 3, and the left-hand arm will have a slope of -3. And we can really just draw them in from that, okay? Oh, you can always plug in some points and check if you need to, but that would be a graph of that initial function right there. And then lastly, let's go to a graph and an equation, or go from a graph to an equation here. So we have a few different things going on. We have a vertex, and then we also have a particular slope as well. And it looks like my slope of my right-hand arm is a -2, okay? And that's telling me that my function got flipped vertically and stretched. So my vertex is at 2, 4, it looks like. So we can go ahead and plug those pieces into our equation. We have y equals a times the absolute value of x minus h, then plus k. So we can throw in our vertex first. Y equals a times the absolute value of x minus 2, and then plus 4. And then it looks like the slope of our of that arm is a -2, and we can tell that it's been vertically flipped. So that confirms that we have a -2 for a. And that would be our final outcome for that guy right there. All right, we got through it. That's a good place to stop.